Today, we will be looking at systems that are larger than 2 by 2, and we will be considering a case in which one of the roots of the characteristic polynomial is repeated. So we're going to be looking again at u dot equals AU, where U is now XYZ, so we have three components now, and A is the matrix 2, 1, 1, 1, 2, 1, 1, 1, 2. So equivalently, this is X dot equals 2X plus Y plus Z, first row, Y dot equals X plus 2Y plus Z, second row, and Z dot equals X plus Y plus 2Z, third row. Okay, since this is a 3 by 3 system, we're going to need three independent solutions to write the general solution, C1U1 plus C2U2 plus C3U3. And as before, we need to find the eigenvalues. And we solve for the determinant of A minus Ki is 0. Now A is 3 by 3, so I is going to have to be 3 by 3 as well. So here I is the 3 by 3 identity matrix. 1's on the main diagonal, 0's elsewhere. You multiply any column vector here by this, and you just get the column vector back. Okay, so this is the 3 by 3 identity matrix. And you'll recall, to find the characteristic polynomial, we calculate the determinant of A minus Ki. And when that's 0, the roots will be the eigenvalues. Okay, so we have our coefficient matrix here, minus K times the identity matrix, and that gives us the determinant with 2 minus K on the main diagonal and 1's every place else. To evaluate the determinant, we need to expand around a row or column. I'm going to choose the first row. It's not the only possible choice. Okay, so 2 minus K is in the 1, 1 position. That's positive, so we have a plus 2 minus K times this little 2 by 2 determinant. Then the 1 here is in the 1, 2 position, which is negative, so we have minus 1 times this little 2 by 2 determinant. And then the 1 here is in the 1, 3 position, which is plus, so we have plus 1 times this little 2 by 2 determinant. And now we just need to do some algebra. This determinant ends up being 2 minus K squared minus 1. This determinant is 2 minus K minus 1. And this determinant is 1 minus 2 minus K. Now, when we do some algebra, we discover that these two terms are both plus K minus 1. And we multiply this out, and we get 4 minus 4K plus K squared minus 1, which is K squared minus 4K plus 3. And now these things give us a 2K minus 1. Now, before we multiply things out, what we want to notice here is that this factors as K minus 3 times K minus 1. There's a K minus 1 right here. I can factor out the K minus 1, which I'm going to do. And what I'm left with when I'm done is this 2 minus K, this K minus 3, and that 2. And now when we multiply this out, we get minus K squared plus 5K minus 6 plus 2 times K minus 1. And now to simplify things, I'm going to factor a minus 1 out of here, and you can check. You get K squared minus 5K plus 4, and that factors as K minus 1 times K minus 4. And we can see what the roots are. K is 4, and K equals 1, which is a double root. The next step is to solve A minus Ki times ABC equals 0 for K equals 4 and 1. And that's going to give us our eigenvectors. Okay, so here is our matrix of coefficients. And the case, here it is again, and the case that we want to do is K equals 4. We put that in here, and we got -2's on the main diagonal and 1's elsewhere. Now the first operation I'm going to do is I'm going to switch row 1 and row 3 to get a 1 into this position, and I like that other one, which is why I didn't switch this one up, but you could have done it that way too. And now let's take this row and subtract it from the second row, and what you end up with is 0, -3, 3. Same idea, take this row, multiply it by 2, and add it to this row, and we get 0, 3, -3. Now, before continuing, you might want to notice that this row is exactly the opposite of that row, so we can save ourselves some time by adding row 2 to row 3, and we've got all zeros across the bottom. Now we take row 2, we want to make this a leading 1, so we divide by 3, and we've got 0, 1, -1 in the second row. And now finally we need to clear the column that has a leading 1 in it. And we do that by subtracting row 2 from row 1. And we've got 1, 0, -1, because -1 and -2 combine to give you -1. And now we are in reduced row echelon form. We can see that the free column is the C column, so we set C equal to T, and now this equation says B minus C equals 0, and since C is T, that gives us that B is T, and now this equation says A minus C is 0, and once again, since C is T, this gives us A equals T. Our eigenvector ABC is thus T, 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 which is just T times 1, 1, 1. Now again, any non-zero real will do here in terms of getting an eigenvector, so we might as well take T equals 1. And that's going to give us an eigenvector of 1, 1, 1. So we're going to have 1, 1, 1 e to the kt as our solution. K, as you'll recall here, was 4. So U1 is the vector 1, 1, 1 e to the 4t. Now we go about this again, and we look at the other eigenvalue, which was k equals 1. And as you recall, this was a double root. So this thing becomes all ones. And now row reduction is pretty easy. Subtract row 1 from row 2, then subtract row 1 from row 3, and we're actually in reduced row echelon form. Here's your leading 1. These are free columns. And there are 2 free columns, so there are 2 free parameters. C is T, B is S, and the only equation we've got is this one, which says A plus B plus C is 0, which, since B is S and C is T, leads to A equals minus S minus T. Now, we look at our solution written in column vector form. A is minus S minus T, B is S, C is T, and we now break that up into the S stuff and the T stuff. And what we can see is that we get S times minus 1, 1, 0 plus T times minus 1, 0, 1. And taking S equals 1 and T equals 0 gives us this vector. And taking S equals 0 and T equals 1 gives us that vector. And these vectors are independent. And the way I can tell that is one of them is not a multiple of the other. Okay, so we're going to get 2 different solutions, one from this eigenvector and one from that eigenvector. So the first one is going to give us minus 1, 1, 0 e to the kt, and k in this case was 1, right? So we got minus 1, 1, 0, e to the t, and then the second one gives us minus 1, 0, 1, e to the t. And our general solution is C1 times our first solution plus C2 times our second solution plus C3 times our third solution, which is C1 111 e to the 4t plus C2 minus 110 e to the t plus C3 minus 101 e to the t. So let me give you a bit of a warning here, because this was a nice problem that I set up. Not all repeated root calculations work out this nicely. And in particular, there are cases where there aren't enough independent eigenvectors for the repeated roots. So specifically, you can imagine a problem where you have a double root, but you might only find one independent eigenvector. That can happen. Such problems are more complicated to solve. And due to our time constraints, we will not discuss such problems.